Let's get going now. So today's topic is vector operations. This is the homework that's due next Thursday. Our learning objectives, and there is this learning objective document that's posted up on Canvas. And these are really important. They tell us what we're responsible for knowing and also gives us a guide of like, okay, what do we need to be able to do by the end of today's lecture? So the first one is just be able to draw and label the features of a vector. And then once we get those general features, and that should be mostly review, we're going to draw some pictures. We're going to use today parallelograms. And so we need to be able to construct or draw this parallelogram from a system of forces and angles. We'll do some examples of that today. Use corresponding angles. So corresponding angles is another key thing there to determine the interior angles. And then once we have those interior angles, we can use law of sines and law of cosines to solve for unknowns in a general triangle. And so these are all posted up on Canvas. I believe I posted a PDF and a Word version. So if you want to like copy it and or add stuff to it in Word, you certainly can. The other thing with these learning objectives is this is what I use when I write exams. And so what I'll do is I'll go through and I'll be like, okay, what learning objectives do I want to test this exam, or which of these are we going to test? And then I basically, the way I wrote them is that I can convert them into an exam question. So I might, an exam question might say, oh, here's a picture. Now draw the parallelogram for me. And so these are valuable in lots of different ways, and you will see these learning objectives every lecture. Next thing I want to show you all is the homework problems. So these are the ones that are due next Thursday. So we know kind of before we start lecture what we're aiming for. If F is given right here, determine the magnitude of the force along AB and also along AC. So we'll talk about problems like this today. The second homework problem, if F is given, determine the magnitude of the force along A and the angle theta. So we can see now we're asked to find a magnitude and also some geometry stuff here. And then the third homework problem, if FAA is given, determine the magnitude of the force along the ABB. There's, under the additional resources on the statics homepage, there's something called supplementary example problems. And you might, if you look under there in this topic, you might find a problem that looks really similar to this. Actually, you're going to basically find exactly the same problem up there. It might ask you for something slightly different. So those I'm doing that intentionally to get you into using those supplementary example problems because they can help you solve the homework on this one. So supplementary example problems on Canvas, take a look at that when you're going through this homework. Maybe you try the problem first without it, and then you're like, oh man, I'm getting stuck. Maybe you can take a look at that. So we're going to start with this lecture example, but actually before we get to that lecture example, let's go ahead and let's get started here with a couple. Let's talk about our first learning objective for vector operations. And as always, right, let me know if there's the screen is blurry or something like that is going on. I also try to, whenever I look to my right, the right side here, I have my second monitor and I'm looking at all the videos and the chat up there. And so if I miss a chat or something like that, feel free to turn on your microphone. And so let's start here with the vector features. And that was our first learning objective, was just to be able to draw and label all the features of a vector. And so if we have a vertical axis here and we have a horizontal axis right here, and I'm not even going to label them an X and a Y. I'm just going to say, hey, it's a it's a horizontal axis and it's a vertical axis right there. And then let's say we have a vector, and we'll do this as a force vector. And so for me in class, most of the time, this is how I do my force vectors. You could use a hat if you want to, if you're used to using a hat, but I like to put the arrow over the top of it, maybe because like they're all forces and they're all like pushing or pulling on stuff right there. And so there's our vector there. And actually, so this is how I'm going to do this when it's handwritten. So in lecture, we'll do it as that the F with the hat over, or the, not the hat, but the arrow over the top of it. In the textbook, they use bold font. So in textbook and also on mastering engineering, they use, so mastering engineering here, they use bold font. Okay, because, and I can't do bold font, right? That would be kind of hard for me. I mean, I guess I can on a computer more than I could like if I'm writing on the whiteboard in a classroom, but in the textbook and so it's just some kind of, just some nomenclature that we all need to know, right? So handwritten, I'll do it like this. And then in the textbook, they do it the other way. The length of these arrows is representative of the magnitude, right? So this is basically representative, the length of that arrow is representative of the magnitude, and we can express magnitude as either just F like that, or we can do it, I'll put the arrow over the top of it and then put the magnitude lines on either one of those there. So our magnitude, right, we'll do as just the plain letter, or I can put the magnitude line. Most of the time, I'll just do the plain letter on that one. Some other important parts of this right here is the orientation, right? So the angle here, so we can call this theta right here. That's our orientation. Just describing, where is that orientation? I forgot a T in there. So orientation right there. And so that just tells us the angle, and that orientation could be from the horizontal axis. It could be from the vertical axis. Another really key thing, especially for us in statics, and I'm going to draw a dashed line and it goes through the vector and it continues infinitely in both directions. This is what's called the line of action. That line of action is going to be key for us all semester. Okay, so this is a really big deal for us. We're going to continue using that line of action a lot this semester. And then there's one more thing I want to point out here, and that's the point of application. And the point of application is just saying, okay, where is that applied? The point of application there, right? Where is it acting? Like, where is that force acting? And so like if I had like a strap here and I was pulling on my hand, right? So here's that force vector. Where's the point of application? Oh, the point of application is at my thumb, right? That's all we're talking about there is where is that force acting, particularly right there. Okay, and that's all the main things we have for the vector features. And so that covers everything that we need to know for this class here. So there's our features, our vector features, or the features of a vector. We've just covered our first learning objective. So we can go back and check off and say, okay, learning objective number 1, we are done with that one now. You'll also notice that I do different colors. If you want to start getting set up for that, I'll do that consistently over the semester. So if you want, I used red, green, blue, black, and then purple is kind of an additional one there sometimes. But if you have red, green, blue, and black, that will cover like 90% of what I typically do. Okay, just making sure everybody's got everything written down here. I'm going to go ahead and I usually like to scroll left to right so that I don't have to wait for people and you can still see what we wrote up last time. So this is our lecture example. What we're doing in this one is we're asked to find the resultant vector here. And we have these two forces. We have an F1 and an F2. And we're asked to find the resultant force of those two. And when I first start talking, I want to talk about what does it mean to have a resultant vector here. If I have like these two forces, right? I have one force that's going up like this, and I have another force that's here. wasn't the resultant force. It's really an equivalent system. It's like, it's a replacement, right? We're taking these two forces, we're taking like F2 and F1, and we're just replacing it with one force right there. And so that's a result. That's what we mean by a resultant vector, is it's really a replacement. We're taking it and we're replacing it with these two new ones. I also made a little prop here of these of this system here. And so I have a 10 or 100 Newton right there. And actually that's 10, I made it 10 inches long. And then the 150 Newton, I made it 15 inches long. And so that's representative of those two forces, right? And so we just want to find the resultant. Now, one way we could do this is we could certainly just find the X components and the Y components, right? And we could break this into components. Totally fine to do that. What I want to do today, though, is actually I want to follow our learning objectives. And so let's break this up into, we're going to use parallelograms, and we're going to use triangles, and we're going to do all of this stuff. So we'll come back and we'll draw this picture here. But before we get there, I want to write down some tools that we're going to need first. So what kind of tools are we going to need for today's stuff? Well, those are the learning objectives. They were the corresponding angles was one of them. So corresponding angles. All we're talking about with our corresponding angles here is like if we have two parallel lines and then we have another thing that's cutting through those two parallel lines, another line, well, this angle and this angle down here, those are corresponding angles. And actually, isn't this angle and this angle, those are all the same, aren't they? So those are all the same angle right there. We could do the same thing with the obtuse ones. You know, the parallel lines could be horizontal, they could be vertical like I drew there. They could also be at some angle like this. So if I have those two parallel lines there and I have some other line cutting through that like that, well, now we know, if I know this angle right here, if I say, oh, well, this is 40 degrees, then I can find that this angle down here is also equal to 40 degrees. So that's all we're doing with our corresponding angles. And then the other tool that we need is the general triangle geometry. And so for this general triangle geometry, and we'll see why we're going to need this, but if we have a triangle, and a general triangle, that just means that we have a triangle that does not have a right angle. Okay, so I'm trying to draw this, so this angle up here kind of looks like a right angle, but let's just assume that it's not. So a general triangle means it's not a right triangle. If it was a right triangle, we could just use opposite over adjacent and adjacent over hypotenuse and all of that stuff there. But if it's a general triangle, which means it's not a right triangle, and let's label our sides here. Why don't we call this side A, we'll call this side B, and we'll call this side over here C. And then I'm going to label the angles opposite those sides with Greek letters. So opposite A, that's going to be alpha. Opposite B, that's going to be beta. And then opposite C, that angle right there is going to be gamma. Okay, so we have our corresponding Greek letters for our regular letters here. And so with this general triangle geometry, the idea with general triangle geometry is if we have three parts, so if we know three parts, with a right triangle, we only need two parts. If we know three parts, we can solve the rest. We can solve for the rest. And we do that using law of sines and law of cosines. Law of sines is pretty straightforward. It's just a ratio of each of the sides and the angle opposite. So like sine, no, I meant to write sine first. So like we could say like sine of alpha over the side opposite, which is A, is equal to the sine of beta over B. We could also say the sine of alpha over A is equal to the sine of gamma over C. And then our last one here would be there's one more relationship, right? Because we've compared A and B, we've compared A and C, but we have not compared B and C. So we could do the sine of beta over B is equal to the sine of gamma over C. And actually you can flip those too. You can put the A on top and the signs on the bottom of those fractions. So either one of those will work. Okay, so law of sines is good. It's three of our potential equations. The law of cosines is typically more powerful, but basically the way I use these equations is I just think, okay, I have 6 equations, and then depending on what 3 parts of the triangle I have, I just go through and I say, I'm looking for an equation that just has one unknown. And maybe I go through law of sines and I say, oh, here's a law of sine equation that only has one unknown. Or maybe I look at all my law of sines equations and they'll have 2 unknowns, and that's why I go to law of cosines. The law of cosines is a little bit longer of an equation. I remember it because it starts by looking like the Pythagorean theorem. But this isn't a right triangle, so the Pythagorean theorem doesn't work, right? But so it's a squared is equal to b squared plus c squared. And then I have to memorize the rest of this. It's minus a 2 times whatever 2 letters show up on the right-hand side of that equation. So times a b times a c. And then it's law of cosine, so it's got to have a cosine in there. So it's minus 2bc times the cosine, and it's the cosine of whatever angle is opposite the letter that showed up on the left-hand side of the equation. So that would be alpha in this case. And then we can write this 2 other ways. B squared, we can start with b squared on the left-hand side. Well, if b squared starts on the left-hand side, then it's a c squared plus an a squared minus 2 times a times c times the cosine of beta. And then I could also put a c squared on the left-hand side. C squared is going to be equal to a squared plus a b squared, and then minus a 2 times a times b times the cosine of gamma. So we have 6 equations. We don't obviously, right, if we're just looking for 3 unknowns, because if we have 3 parts and there's a total of 6 parts of that triangle, if we already have 3 parts, and we do need to have 3 parts of a triangle in order to solve for any of the other parts. If we don't have 3 parts, we can't solve for the other parts. So there's 6 equations, but obviously we only need 3 of them every time, right? At most 3 of them every time. Sometimes we know more than 3 parts of the triangle before we go into our general triangle geometry. Okay, so let's jump into now our example problem. And I'm going to work all of the examples in lecture according to the same format that you have to do on the handwritten homework. And that's given, find, solution format. And everything needs to be vertically stacked, meaning you can look at the notes and you can say, I know exactly what order you wrote stuff down in just by going from top to bottom. So given in this problem statement, and I'll go back to the picture here in a little bit, but they gave us a, and so this is our, actually, let me go back right now to show you this right here. So we have this, right? We have this resultant. They're asking us to find the resultant force vector. So we're going to draw all of this given information here. I do want to point out one thing. Look at these little dashed lines right in here. If you look right in here, right there, you can see those dashed lines and they're pointing right back there. So we're already seeing the line of action, right? Remember that line of action extends infinitely in both directions. So we're already seeing this line of action starting to show up And we see that they both intersect right there at the origin of that coordinate system. Okay, so just wanted to, that's the problem we're working. Oh, I also want to point out too, this is example 2.1. This is one of those suggested example problems to look at. And so part of the reason I'm doing this is to emphasize the the value of those example problems that are in the textbook. These will help us in understanding how to solve the problems here in class. Okay, so given here we have a vertical line that they drew. They drew a horizontal line for the vertical and horizontal axes. And then we had a, going off and to the right, we had 100 Newton angle or 100 Newton force. And so I'm going to draw that one, about that long right there. Remember the length, and this is F, what they called F1, is equal to 100 Newtons. And so the length, remember, is the length of the arrow is representative of the magnitude. And then we had another one that was up here, and I'm going to draw it a little bit longer because that was 150 Newtons, and that's what they called F2. Oh, and I see a question here that I missed. For the law of sine, shouldn't it be the inverse? Oh, you can flip them, Ricardo. You can do either way. You can put the sign on the top, or you can put the sign on the bottom. It doesn't matter where they go. And I see Sean answer that question. Thank you, Sean. Okay, so now, and then they gave us these angles here. They told us this angle right here is 10 degrees. And then this angle right here, that is equal to 15 degrees right there. And what they want us to find for this problem is the resultant force vector. And so if it's a vector, right, that just means that it has magnitude and also direction on there, or orientation, however we want to call it. I guess I call it orientation when I wrote the features of a vector, but we can also call it the direction as well. Okay, so we have the resultant. We're asked to find the resultant force vector. So now the next step here is our solution. So this is the format that you'll write, that you'll do your handwritten homework in. And actually the handwritten homework, if all you do is write like FR is equal to, whatever the answer is, that's all you have to do for your handwritten homework. That's all the rubric says. You would get 100% for just doing that. If you want to put more in there, and most students do, if you want to put everything like we're going to put in here, then you're certainly welcome to. It'll help you study for the exam. It'll help you figure out when you don't get the right answer on the homework, right? So there's lots of different reasons to put more in your solution, but the rubric very clearly just tells you, hey, just do, all you have to do is follow this given find format. There's a specific header formatting that we're asking for, and all these requirements are posted up on Canvas. Also for the first two, if you're not quite sure, how to interpret the rubric or something like that, for the first two handwritten homeworks, if it looks like you're trying, you'll get full credit. The graders know that the first two times is all about feedback. And so we'll say, hey, that's not the right way. Please change this, but we're not going to take off any points as long as it looks like you're trying. Obviously, if it's like, doesn't look like you're trying, then we're going to take off points. But as long as it seems like you're trying, then, we're going to, we won't take off any points there. So solution then, we're going to do this. We're going to use parallelograms. Okay. Now I talked about before that you could certainly do this by breaking it up into X and Y components. When we're given two forces and asked to find a resultant, it is easier to break it up into components. Okay. But our next problem that we're going to do, it's going to be easier with parallelograms. Now, I don't like to contaminate my given information. So we're going to draw this picture again, and make sure you draw it nice and big. As students, as in engineering, don't be afraid to use a little bit more paper. I know sometimes the tendency is like to save paper, right, and to cram things down. This is the chance to draw it big so that we can see it easily. This is a chance to give you feedback, right? Not when you get your first job and your boss is like, hey, that's not the right way to do it, right? You're paying us to give you feedback and to teach you. And so, draw it big so that you can see exactly what's going on. And so we have our X and Y axes. I'm going to draw F1 down here, and that's at a 15-degree angle. And then we have F2 is up here, and that's at our 10-degree angle, and it's going to be a little bit longer right there. So let me go ahead. F1 is equal to 100 newtons. Now we're going to fill in up here, okay, up, kind of in between those two F's. So I'm going to draw my F2 over here off to the side, out of the way there. Let me also add my geometry here. So this is 10 degrees, and this is 15 degrees right here. When we're doing our parallelograms, let's write down some steps here. I'll do that in purple. Okay, so our steps. The first step is tip to tail. All right, right now, if we look at our problem, and so when you're doing this, identify where everything is touching. Right now, everything is touching right here at the origin, right? All the tails are touching. And so here I have my yardsticks, right? So what we're going to do to get tip to tail is we're basically going to draw lines that are parallel to those original lines. So here I have another segment of yardstick. It's the exact same length as the 100 newtons right there. They're all touching at the tail. So what I'm going to do is let's move this up to the tip. And so we'll do that one. We'll move it up to the tip. And then I've got the same thing over here. I've got another segment of yardstick. It's the same as this original one. And I'm going to move that one. I'm going to move it up to here. Now that we did tip to tail, and basically that's just drawing lines that are parallel to those original ones, now I have my parallelogram. And then the resultant, doesn't the resultant go from here to here? It bisects that parallelogram. Okay, so let's draw F1. Let's draw a line that's parallel to F1. There's our F1 and about the same length right there. And then we have this, or maybe I need to draw, sometimes it takes me I have to kind of extend them a little bit so it looks pretty good there. So there we just created our parallelogram, and we know this one right here, that is F2, right? And this one over here, that is F1. And then our resultant is going to bisect the two of those. So there's our FR. And now look what we have. We have two triangles. All right, we have these two triangles. We only need one of them in order to do the general triangle geometry. Okay, so step one was really our tip to tail stuff. And it could be tail to tip, right? All of our tails were touching, but notice now where F2, like right here, right, I just highlighted that, right? Now we have F2 tip to the F1 tail. Also remember we talked about how the resultant force was like an equivalent system. And another way to think about this is like giving directions. Like I could tell you, like if you were, if we were on campus and you're like, oh, how do you get to the library? Say we're in Marcus Hall. I could just say, go that way 500 feet. And that would be like the resultant. Or I could say, oh, you have to go up, what would that be? You have to go up like 15th Street, and then you're going to take a right on Illinois. That would be the components, right? That would be like going along, here you're going along F2, and then you go along F1, or you're going along F1. So they're all equivalent systems. They all get us to exactly the same point. Another way to think about that is if we were in class and I was like, okay, if I had somebody that was a robot and they were just holding on to the strap, and they didn't know if I was applying F2 and F1 or if I was applying the resultant, they would not be able to tell. They would think to them, it would feel exactly the same whether it was the resultant or if it was F1 and F2. Yes, Colin.
Just wanted to go back like a step before that. So the line of action where those two meet is always going to be where we're basing our graph off of, right? So that's always going to essentially be the origin.
Yeah, but actually, if you look at these other ones, like this one, your homework problem, there really is no line of action in there. You don't have to worry about that. Like, oh, these ones, I guess you could kind of extend the line of the line of action, right? And where they both meet. Yeah. So in some of your other homework problems, you might have to deal with that line of action, but you may not also. But we can extend that line of action. We can use any point on that line of action. Okay, we don't have to use the point of application. Great question. Thank you for that question. Okay, so step one was tip to tail. So now what can we do here? Now the next thing that we need to do is actually we can use our corresponding angles. And the corresponding angles is what's going to help us find the angles for the triangle, because it looks like, and we can use either one of these triangles. We can use the one on the top left or the bottom right. They're the same triangle. And they're going to get us the same information. So we can use either one of those. Now, if we do, I'm going to switch to blue here, our corresponding angles, like, how about this 10 degrees? Basically the idea of corresponding angles is to transfer information from one side of a line to the other side, and using those parallel lines. So this 10 degrees, wouldn't that, if I drew a line parallel to my vertical axis, wouldn't that one right there also be 10 degrees? Right there. And then how about this 15 degrees? Where does this 15 degrees show up here? Well, 15 degrees is measured from the horizontal. So doesn't that mean that this right here would be 15 degrees there? And then we know that these two are 90 degrees apart, right? Because the horizontal and the vertical has to be 90 degrees apart. So now that we know that angle, right? We know the angle is just going to be the sum of 10 plus 90 plus 15. We know F2 and we know F1. Don't we have three parts of that triangle right there? And so we use our corresponding angles. And then our third step here is going to be to do our triangle geometry. And I guess technically that's our general triangle geometry. And so let's go ahead and draw. I'm going to pull out that triangle there. So let's draw that triangle. And so we're going to have, I guess I'll do it in red. So I've got that side there, and I've got this side here, and then I've got the resultant that's right there. We know this side is 150 newtons. This side is 100 newtons. And we have this angle right here that's 115 degrees. So don't we have three parts of a general triangle? And that means we could find like this side over here. We can call that alpha. We can call this side right here beta. And then this side right here, that's going to be FR. That's getting to that spot is really the hard part. Getting that triangle is really the hard part. And also the other thing about statics, we're going to talk a lot about the steps. Okay. And so that's something that I want you to be able to apply to your homework problems now. So how can we apply these same steps to get to this point on another problem? So, the steps I've written down are kind of general. So you may want to add to those and say, oh, okay, well, I need to think about this a little bit more. Or sometimes I need to do this. So there's other parts of that we need to, that you're going to need to add to. I also want to point out something else over here as well. And I wonder if some people thought about this. Can we take, what's this entire angle right there? Wouldn't that be 90 minus 10 minus 15? So that would be like 65 degrees. Is that 65? Could we say that 65 degrees? Can we say like half of it is here? No, right? Okay, so watch that. This is not is not equal to half of 65 degrees. Okay, now we could use that 65 degrees though, because for the whole parallelogram, don't we know if we have 65 here, if we have 65 up here, then we could have also used that method to find the 115 degrees as well, because we know take our 360 minus 65 minus another 65, and then whatever we have left over has to be divided equally between this angle up here and this angle down here. And we would have found 115 as well. Okay, so we can do it that way as well. Now, our next step here, and we'll put one more step up here, number 4. This is the law of sines and cosines. And when we're doing law of sines and cosines, what we're dealing with here is just, I'm just going to go through all those equations and I'll say like, I usually start with law of sines and I just say, okay, what about A and alpha? And then I can use 150 and beta. Oh, actually that's got 2 unknowns. Okay. So I start going through and I just say, I'm looking for an equation that only has one unknown. And so I'm just a process of elimination is all I'm doing, is just saying, what about this equation? What about this equation? When we go through that, what we're going to find is its law of cosines. FR squared is going to be equal to 150 squared plus 100 squared minus 2 times 150 times 100 times the cosine of the angle opposite that, which is 115 degrees. When I plug this in, we're going to find that FR is equal to 212.55 newtons. Okay, so now we've got 212.55 newtons. Mastering, they want everything in 3 sig figs. So we would do 213 newtons for mastering engineering. I think they just tell you to enter it in 3 sig figs. I don't think they take off any points. But we do 3 sig figs for mastering there. And then we could also then, at this point, now we can actually use the alpha, the sine, law of sines here. So we can go sine of alpha over A, which the opposite side of that, which is 100 newtons. And that's going to be equal to the sine of 115 over FR. Now, I'm going to use anytime. Now, you might enter 213 into mastering, but for calcs, I'm going to go back. For calcs, we're always going to use unrounded values. Okay, so we go back to the 212.55 and we'll solve for alpha in this case. For this problem here, let's see, I did 150. Oh, I actually solved, in my notes, I actually solved for beta. So I don't have alpha here, but I bet we could do it. I bet I could figure it out here real quick. So sine of 115 divided by 212.55 times 100, and then the inverse sine, 25.24. Okay, so we find here that alpha is equal to 25.24 degrees. Yes.
And then, so we're going to add that to the horizontal axis, or could it be in any orientation?
Yeah, you know what? For this example, I didn't specify, but if this were a homework problem, we would have to specify, specify the angle from the horizontal or specify the angle from the vertical, right? Because right now, yeah, I'm just specifying it from the 150. But if we wanted it from the vertical, wouldn't we just add 10 degrees, right? And that would tell us the angle. Yeah, and I kind of in some of my lecture examples, I leave them a little bit loose like that, where I'm more focused on, getting the main parts of it done. But absolutely, call
Cool.
we need to, yeah, based on what and I think the actual example 2.1 does tell you specifically what to do.
Sweet. Thanks.
Yeah, everything is in degrees, Caleb. I see the question in the chat. I'm doing everything in degrees. Yeah, we're only going to do one thing in radians, and that'll be a way end of the semester. Everything is absolutely in degrees here. Good question. Okay, and I know I'm pretty much out of time here. I did want to point out this other example 2.2 now. So what we're going to do with this example and what they do here, and you're probably not going to have time to write this down, but if we think about this, what's in our steps, we have this axis here, and I'll do it in red. We have this other axis over here, and I'll do it in blue. Well, notice everything is touching at the tail again, right? So step one is tip to tail. So I'm just going to draw this red line here at the tip of that 600. And then I'm going to draw the blue line at the tip of the 600 and parallel to that original blue line. Do you see how all of a sudden now I have the parallelogram and we have two triangles as well? Okay, so take a look at that example 2.2. They go through the full solution there.